Hey everybody, I'm happy to welcome you to our webinar today. I'm Andy Zimmerman. I'm the Chief Technology Officer here at Grace Technologies, and I'm super excited to be presenting on kind of a new topic for us, but one that's been near and dear to my heart over the last kind of decade plus, and one that certainly is exciting right now, given kind of the state of technology over the last kind of 6 to 12 months, and that is navigating the artificial intelligence revolution, specifically with respect to industrial predictive maintenance. So before actually I kick in, let me just touch on a couple of things. First and foremost, at any time, I want to encourage you to ask questions via the chat interface. We're not going to answer those live during the actual presentation, but at the end, I hope to have some good set of time to address those questions as they come in. Additionally, because of the kind of wealth of content that got developed for this webinar, Nick and I decided to split this into 2 sessions. So we'll be presenting part 2 of this webinar on Thursday. And after that, we'll be sending out an on-demand copy of kind of the 2 parts put together. So with that, I think that's all the housekeeping. I'll kick off here. All right. So just a little bit of background about who I am. Again, my name is Andy Zimmerman. My background actually comes from a kind of strange place. I did my PhD at the University of Michigan, studying in civil and environmental engineering, and I was building kind of artificially intelligent wireless sensor systems that were designed to monitor civil infrastructure, so bridges, ships, wind turbines, that sort of thing. That thesis work was all focused on distributing data processing tasks throughout those wireless sensor networks. And I moved from there. I started a company back in 2009 to really take that technology and focus it commercially on structural health monitoring and predictive maintenance or IIoT kind of technologies. So that company, Civionics, I sold in 2018 to Grace Technologies, and through kind of a complicated thing I'm not going to explain, we created a subsidiary called Perceive. So I'm super excited today to be able to put on the Perceive hat and really talk about a lot of the work we've done over the last 4 years building AI and kind of software-based analytics that sit behind our GraceSense line of technologies at Grace Technologies. All right, so before I get going, I really do also want to call out to my collaborators in the AI space. Over the last 4 years or so, I've collaborated heavily with Iowa State University and Dr. Chow Hu, who's pictured here. We've done quite a bit of work developing algorithms to predict bearing failure in rotating equipment. And you can see here that we've had funding from the state of Iowa, from Grace Technologies, and then most recently from the National Science Foundation. That's really funded a lot of our comprehensive research in this space. So I'm not going to get into a lot of the details of that grant work here in this presentation, but I just want to set the stage for some of the background for why we're talking about this today. All right. So why is this webinar happening today, and why is now the right time to have this particular discussion? Well, first and foremost, AI is an incredibly significant topic right now. Both artificial intelligence and machine learning are really poised to transform the entire landscape of predictive maintenance. And ultimately, what we're talking about when we're doing that is drastically reducing downtime and kind of alongside that, reducing our overall cost of maintaining assets in the industrial world. The rate of rapid technological advance over the last kind of 4 or 5 years has been incredible. And that pace of innovation in both AI and ML is kind of constantly accelerating with new applications and new kind of technologies emerging, almost every day. So again, now's kind of the time to have these discussions. On the backside of those new kind of opportunities that are arising, we're also seeing new challenges. As industries kind of start to incorporate AI and ML into the way they work, these challenges are going to present new hurdles that we need to figure out how to kind of navigate around. So things like, how do we manage data? How do we deal with the implementation costs and management of AI and ML systems? And then how do we keep the data that we're now collecting and the analytics that we're now providing private in kind of a cyber secure way? And really, lastly, the future is now. I mean, if you've seen any newspaper over the last 6 months, AI is all over the place. It's becoming really prevalent in the commercial sector, and certainly industry is kind of poised, specifically in the predictive maintenance space, to take advantage a lot of these new AI and ML technologies. So before I get going, just some brief expectations for what I expect to get out of this next kind of 30 to 45 minutes. I'm expecting that most of you watching this webinar are coming to this from the perspective of industrial maintenance. So you're not an AI expert, you're coming from the kind of more industrial perspective. You see the potential of how AI can transform the way that you do business and the way that you maintain your assets, but you still have some questions about how artificial intelligence can really play within your existing ecosystem and how best to use these new technologies to benefit your business. So what you can expect from this webinar and from me, first and foremost, this is a huge topic. As I mentioned before, we really found we can't cover it in a single webinar, so we're going to spread it out over 2 parts. And really my attempt is to provide a comprehensive overview of the topic. We're not going to go into a tremendous amount of detail on any one thing. So I'm gonna kind of position this as an AI ML in predictive maintenance 101 class. I'm really not targeting AI experts here. Again, I'm going to try to keep this very surface level, very easy to interface with for people who don't necessarily know the nuts and bolts of what's happening under the surface. And I'm also not going to be product focused here. We'll do a little demo at the end of this first part of some neat stuff that I think we've been working on over the last 6 weeks or so. But in general, this is just an informative webinar. Hopefully I can give you some good content here to help you navigate artificial intelligence in this industrial space. All right. So there's not a lot to the 2-part webinar in terms of subsections, but I'll start by focusing on maintenance as a whole and how that's evolved, and then talk about how artificial intelligence and machine learning can jump into that maintenance space and make a big difference. We're then going to talk about a new product offering we're getting ready to release called Foreman XAI. That'll be a brief demo kind of at the end of this part. And then on Thursday, we'll dive in a little bit more detail and talk about AI concepts in a little bit more depth, and then get to the back end of that webinar and talk about specifically some challenges and some opportunities that are presented by this wealth of technology that's been emerging over the last couple of years. With that, let's jump into the evolution of maintenance. So from day one, when we started maintaining our industrial assets, we're really trying to do a real simple task, right? We're trying to keep our factories running. And in order to do that, we follow a pretty simple formula. First and foremost, we need to find out when things go wrong. And then when we find that out, we need to fix the problem. And ultimately, we're looking in the industrial maintenance space to keep that particular problem from happening again. So regardless of our approach, that's ultimately what we're trying to do. And the goal over the last 40, 50 years is to make that process more efficient, right? Can we identify problems faster? Can we fix problems more easily or more inexpensively or more quickly? And can we eliminate downtime entirely, right? If we can do all those things, we're sitting in a really good place. And I've kind of broken this down. You may have seen me talk about what we call the maintenance spectrum before, but I've really broken down today's discussion into these 4 topics where we start with corrective maintenance, we then move into a preventative space, bring that into a condition-based monitoring kind of ecosystem, and then move that into the predictive space, which is really the core of what we're going to be talking about today. So I'm going to spend a little bit of time talking about these four things before we pivot and really dive into the AI content. So to start with, corrective maintenance. This is your most basic type of maintenance in the industrial facility. Oftentimes we call this reactive or breakdown maintenance or run to failure type maintenance. And this generally is just involves letting something run to failure and then fixing it when it fails. This is a good approach in a lot of cases. Still, even today, with all the AI we have, it can be used when equipment failure really doesn't provide a significant impact on your business, or it doesn't lead to any sort of secondary failure once that piece of equipment goes down. And we typically apply it to non-critical assets. So the big example here would be, I don't know a lot of folks who have condition monitoring or predictive maintenance technologies sitting on their light bulbs, right? When we change a light bulb, we just wait for it to go out, we put a new one in. So this has some advantages. Number one, it's inexpensive to implement. There's no upfront costs really, as you only take action when something bad happens. It's suitable for equipment that has unpredictable failures because we kind of just wait for something to fail and then we fix it. From a kind of infrastructural perspective, it doesn't take much planning to implement a corrective maintenance program compared to a preventative or a predictive maintenance system. But on the downside of that, there's the potential for high costs. A lot of times if we have unplanned downtime, that can really drive up a facility's costs. If we have to bring in labor urgently to fix something, that's more expensive than planning it out in advance. And then obviously, if you have a failure that you're not expecting and it causes something else to fail as well, that cost of replacing or repairing the equipment that's gone down can skyrocket. So we really, with this approach, have a increased risk of problems. So generally, the next step in the maintenance paradigm is to move on to a more preventative maintenance approach. So this is often talked about as schedule-based or planned maintenance, and it typically is going to involve some sort of routine inspection of your equipment, coupled with some sort of manufacturer's guidelines on how often something should be maintained. And the idea is that this regular cadenced maintenance structure will give us the ability to prevent failures before they occur. This is often used on assets where we really well understand the failure mechanism of that asset, and we can anticipate kind of how things are going to degrade. It's really well positioned for critical assets where failure can lead to high downtimes, high disruption, high costs, because the idea here is we're getting out in front of the failure and we're fixing things before they go wrong. The big example, both at home and in the industrial space, is just changing oil regularly in order to prevent engine wear, right? We do that on some sort of schedule that's set in combination of what the manufacturer recommends and how hard you're running the piece of equipment in which you're changing oil. So the advantages of this sort of approach is that it does reduce the likelihood that you're going to see unplanned downtime. If we're maintaining ahead of time, we're generally not seeing unexpected failures, or at least that's the hope. It will extend your equipment's lifetime because we're not running that equipment in a degraded state. We're typically in a healthy state because of that routine maintenance. It also allows a facility to really do a good job of budgeting their maintenance dollars. Their costs are predictable. It allows us to do an advanced kind of budget assessment, and it keeps the dollars and cents in a little bit more formulaic manner. On the flip side of that, though, it can lead to unnecessary maintenance. If I'm maintaining something once a month and not using that asset as frequently as maybe we used to, we're probably over maintaining that because it's just based on kind of average use and expected life cycles. It really does also require a good understanding of the equipment itself and how that equipment runs in order to effectively schedule out the cadence for maintenance. And lastly, this can be pretty resource intensive because it requires both planning and it requires the actual laborer to go out and do these routine inspections and perform maintenance on a regular cadence. So over the last kind of decade, where the industry has really been pushing towards is implementing sensors to get us to a phase where we're using what we call condition-based maintenance approaches, right? This is where we take those sensors, we monitor our equipment, we grab data from that equipment that can be indicative of problems that might occur during normal operation, and then we use that data to detect problems before failure occurs in our asset that we're trying to monitor. We generally see condition monitoring used on very critical assets or complex machinery that has kind of a regular operating condition. So it's running in more or less the same way generally. And we know more or less how the piece of equipment is prone to failure. So this is especially effective in places where that downtime of that equipment can lead to significant costs. And the reason it's effective there is because this is a more expensive approach to maintenance than kind of just doing a preventative or a wait till it fails kind of approach. So the good example here, and we at Grace, sell products in this space, is using vibration monitoring devices or sensors to detect the onset of bearing damage, right? We can use increases in the amount of vibration that we're seeing and the way that that vibration is happening to drive early maintenance that prevents the actual downtime of the piece of rotating equipment. So condition-based maintenance has a lot of advantages. It, as I've mentioned, drastically can reduce your unplanned downtime. It allows us to schedule maintenance work ahead of time because we're using kind of a data-driven approach to when things need to happen. And generally, this is going to increase the overall lifespan of our equipment because we're detecting issues earlier, and therefore the repairs or the maintenance is done in such a way that we're not running a piece of equipment in a damaged state generally. However, on the flip side of that, this is typically something that requires investment, both in specialized tools and in technology and in training, right? In order to effectively implement a condition-based monitoring solution, we need expertise in data analysis and data interpretation, and all of this becomes, can be expensive and hard to maintain, right? So it does require constant attention and maintenance, but it sets the stage nicely, this condition-based monitoring paradigm, for what we're talking about with the rest of this presentation, which is truly predictive maintenance. So the question that I'm going to phrase in this particular slide is, how can AI impact the maintenance world that we just discussed? And it can do this in kind of a variety of ways. First and foremost, I think AI is really the stepping stone through which we can get to a true predictive maintenance world. A lot of folks talk about predictive maintenance when they're talking about condition-based maintenance, but really when we're predicting something, we're truly looking into the future and trying to see when a particular asset is going to fail, right? So what AI can do is it can come in, it can help analyze patterns in data and help predict failures, hopefully long before they occur. So whereas condition-based maintenance is really looking at when that data exceeds some threshold, the predictive piece is going to say, hey, I know when that data is going to exceed that threshold, and that's at some point in the future. So we're getting an additional lead time before we need to go in and maintain that piece of equipment. This also allows AI to come in and use historical and real-time data together to suggest possible remediation actions when something does go wrong. So we can leverage that artificial intelligence as a sort of co-pilot to aid in our preventative measures, both before an incident occurs and then once the failure or the equipment degradation has happened. It helps us to efficiently or potentially optimally allocate our resources. So that artificial intelligence can come alongside kind of the maintenance team and help prioritize maintenance tasks based on urgency and importance in a way that will lead to hopefully an optimal allocation of resource in the facility and an ultimate cost effectiveness of the maintenance program. And then lastly, and this is pretty important, almost every customer we talk to has a difficulty hiring and keeping personnel that are both experienced and skilled in the maintenance workforce. And there's a lot of kind of reasons for this, but we generally find that most industrial customers of ours right now are short-staffed, and that staff may be undertrained or at least underexperienced. And so I think that one thing that artificial intelligence can do for the predictive maintenance space or maintenance in general is provide a true intelligent partner that can assist that maintenance workforce in that may be lacking personnel and experience, and assist that workforce in maintaining the equipment that exists in really any industrial facility. So from there, let's talk about this topic of AI. What is artificial intelligence? And there's a lot of ways that we can define this, but I'm going to just kind of very simply lay this out as artificial intelligence is always going to come from a computing system of some sort. And it's going to be capable of learning from data, be capable of taking that data and then making decisions. And ultimately, we're using it to perform tasks that generally, at least historically speaking, have required a human level intelligence to perform. Right. So at a high level, we're using a computer to do something that previously was impossible without a human in the loop. Right. There's a lot of applications here, and we're going to talk about these later, so I won't touch on them. But generally, predicting maintenance or machinery failure, recommending maintenance tasks, interpreting images, all these things. This all falls into the big bucket of artificial intelligence in the maintenance space. All right. So what I'm going to do now, we're going to lay out a handful of artificial intelligence applications that apply to the predictive maintenance space. And we'll just walk through each one of those, and I'll give you a little bit of color on the sorts of things that AI is well positioned to do over the next few years in really any industrial facility. We'll start with image recognition or computer vision. So image recognition is generally a subset of what we call computer vision. It's a technology that's going to come in and help identify people, places, objects, possibly writing, other things that exist in images. And that image could be either a still image, a photograph, or video. So this involves processing and interpreting that visual data, and then we take that data and categorize and label what we find in that data. So, you know, the big example that I see that you may have seen kind of in the main media is when you look at a self-driving car, you see a lot of times that we've got these boxes surrounding objects that car is passing, and that's the AI identifying that object and then classifying it as a human or a dog or another car, right? So the capabilities that are key to image recognition, first and foremost, identifying the presence and the location of objects within an image, right? That's the drawing of the box. We can classify those images. So we can take that image, break it into pieces, and then classify parts of it or the whole thing into certain categories. So is this a picture of a bird? Is this a picture of a plane? Is this a picture of Superman, right? So facial recognition is another big topic in the use case for image recognition, where we're able to identify and or verify a person's identity just using their facial features. Lastly, we can leverage image recognition to take text, an image of text, either written or typed, and then identify the characters that are on there from either an image or a scanned document of that text. And when we bring all this together, we can do a lot of kind of really advanced things. So that the common example of this AI and kind of everyday use cases is Facebook or any one of the social media platforms taking a photograph and then automatically tagging who exists in that photograph. We've all seen that technology play out quite a bit in kind of our day-to-day lives. But then when we move that into the industrial facility, we see that there's tremendous application for this AI there as well. So first and foremost, we can use a similar facial recognition to aid our kind of security measures. So we'll either in surveillance or potentially using facial recognition to enable access to certain parts of the facility that may be otherwise off limits to the general populace. We can use image recognition in the kind of AGV or autonomous vehicle space to identify objects, signs, lanes, just to increase the navigatability and safety of those autonomous vehicles. We can use AI in the image recognition world to visually inspect assets. So this would be using either video or still images to search for signs of damage or decay in our industrial equipment. And then lastly, and this is kind of related to the last one, we can use this to augment some existing technologies. So thermal imaging is typically used to detect the presence of heat in some sort of rotating or electrical equipment. And that thermal imaging can be coupled with image recognition to actually pull out signs of impending failure in pieces of equipment that could potentially overheat. That's just kind of an overview of how image recognition can impact the predictive maintenance space. So I got one more, drone inspections. So this is, again, coupled with this idea of doing a visual inspection using an artificially intelligent partner. Here we can put a drone, either a flying drone or potentially a robot that's ground-based, into potentially dangerous areas to do inspections for us and use the AI to kind of automate some of that analysis of the imagery that's coming back from that drone. All right, so the second application that I'm going to talk about is predictive analytics. And again, this is a big space. This can encompass a lot of things. But in general, what we're talking about is leveraging either statistical techniques or full machine learning approaches to analyze both current and historical data in order to predict future outcomes, right? So the idea is that these technologies are going to aid us in understanding both kind of what's happened in the past and then using that understanding to predict what most likely is going to happen in the future. And obviously that creates tremendous value for how we maintain our facilities. Predictive analytics, from a key capability perspective, forecasting is the big thing, right? That's predicting a trend over time. Now, if this worked perfectly, we'd all make a lot of money on the stock market. Unfortunately, not all data trends can be predicted, but fortunately, in the predictive maintenance space, we can leverage forecasting in a lot of ways to look at where data is headed and when it's going to create a situation that requires maintenance. We also leverage predictive analytics to do classification. I talked about this a little bit earlier, but basically we're taking data and then we're predicting the category to which a certain data point belongs, whether that's an image or a sensor trend. We want to do risk assessment in general with predictive analytics, and that's tying all this together to estimate the likelihood of a given outcome, right? If we can forecast into the future different possible scenarios and then assign probabilities to those scenarios, we can leverage that to kind of do a risk forecast for how important it is that we do certain maintenance at different times. And then ultimately, what we're looking to do with predictive analytics is optimize decision making based on the different data sources that are coming into the predictive analytics engine. So the common example of this that you've seen in your everyday life is through Netflix or any sort of streaming service that's going to use your pre-existing behavior to predict what kind of things you might want to view in the future, right? So whether that's what things you've bought, it's going to predict what sort of things you might want to buy, or what things you've watched or listened to. We can leverage these algorithms to kind of give suggestions for what an individual might be interested in seeing or viewing or listening to in the future. In the predictive maintenance space, this has a lot of applications. We can use predictive analytics to establish a baseline, kind of a standard operating behavior of a piece of machinery, and then use that baseline to issue alerts when we see anomalous behavior happen, right? So this is an important thing for detecting anomalies and engaging a maintenance team early. We can do remaining useful life prediction. We can take data and predict how long a piece of equipment has until it starts to fail based on historical data. And then ultimately, I talked about this on the last slide, we can use that information to do a risk assessment and associate a given risk with different types of failure, which then allows us to prioritize what we do on the maintenance side based on those risk profiles. All right, so let's move on to some of the more kind of novel recent AI technologies, and I'll start with natural language processing. This is a branch of AI that's going to give a machine the ability to read, understand, interpret, and derive meaning from human language, right? So this takes ideas from computational linguistics and then couples it with machine learning or deep learning techniques to give this sort of ability for a machine to understand what a human is saying. This is used in a variety of ways. First one is sentiment analysis. That's looking at a piece of text or a portion of speech and determining kind of what the person means by that. So an example would be, is this tweet a positive or negative reaction to some event, right? So sentiment analysis allows us to extract subjective information from source materials. We can classify text into different organized groups, and that plays out in a lot of different ways. We can do machine translation, right? That's your interpreter. When you take English and you convert to French, and then from French to Spanish, that's an understanding of either written or typed text, and then bringing that from one language to another. And lastly, speech recognition, that adds the written or typed capabilities and brings in the ability to interpret spoken language as well. All right, so the common example here that you've all interfaced with is the digital assistant, right? Whether that's Siri or Alexa or the Google Assistant, these are all using natural language processing to both understand and then set the stage for responding to voice commands. In the predictive maintenance space, we can use this sort of natural language processing to read and interpret things like maintenance logs, maintenance records. We can identify patterns that come out of those and alert to potential issues based on anomalous behavior in that text. We can use this to set the stage for intelligent assistants, right? These are, think of them as chatbots, and this is the technology that enables us to build those chatbots in a way that it's going to understand what we say or what we type, and interpret those kind of commands in a way that allow us to automate some of the feedback that we give a given user. And lastly, we can really benefit from natural language processing in the training and safety world. by taking safety protocols and training manuals, and then allowing the natural language processing to create kind of an interactive environment for training an individual. And I'll talk about this a little bit more in the next application, which ties really tightly to natural language processing. And that's generative AI. This is the one that you've heard about probably over the last 6 months in great detail. This is where we're taking systems, AI-based systems that are capable of generating new creative content or new data that matches the patterns of some sort of input data that we're providing it, right? And this gives the artificially intelligent agent the ability to create things like image or text or music or any sort of other form of creative output in a way that's authentic and original at the same time, using the data set that we're training that system with. This allows us, again, to create content of a variety of different sorts. It lets us augment data. I'll talk about this on the next slide, but the idea is we can take synthetic data that's made by the AI and use that to augment real-world data in cases where we don't have a lot of real-world data to go with or to use. And then lastly, we can use this to simulate realistic scenarios for both training and testing purposes. All right, so a common example of this, the big one over the last 6 months, has been OpenAI's release of ChatGPT and the GPT models that sit behind it. These have allowed humans really to interface and create human-like text based on some sort of given prompt that you put in there. And I'm not going to go into a lot of detail on that because I'm sure you've all seen this in action, but this sort of generative AI can have tremendous impact in the predictive maintenance space. And I'll talk about these kind of 2 or 3 different ways in which I see it impacting. Number one, synthetic data generation. I just talked about this on the last slide, but a lot of predictive maintenance requires a lot of failure data. And in the industrial world, sometimes it's hard to gather failure data. So if we can actually take the failure data that we have and then augment it with synthetic data, we can create predictive algorithms that are significantly more impactful. We also can use generative AI to simulate different scenarios. So this is going to generate a creative scenario where a piece of equipment fails in a certain way and then help understand and train around potential issues that might occur in the predictive maintenance environment. We can also use generative AI to generate predictive models. So these are going to kind of autonomously build out machine learning models that can do a better job of predicting equipment failure than the ones that came before. And then, lastly here, we can generate additional normal machine data that can help detect anomalous behavior. So this is very similar to the synthetic data generation piece, but allows us to kind of pivot that and look for anomalous behavior in our assets. The one that's not on here also is this is the natural extension of kind of that chatbot interface, right? Where we use natural language processing to interpret what the human is saying, and then we use a generative AI to position a response that sounds very human-like back to that human. Okay, I think this is my last application here, and that is digital twin. So you may have heard this kind of term bandied around in a variety of different ways. Generally, we're talking about creating a virtual model of a process or a product or a service or something, and it's going to serve as a mirror of that thing in the real world. And we use sensors on the real thing and data that comes from those to reflect the state of the real world in that kind of virtual environment. So this is kind of defined in a variety of ways. We can use this for simulation and testing. We can model how a system may respond under different conditions without actually risking the real system, right? We can fail the virtual model without actually failing the physical asset. We can optimize our performance. So we can analyze data patterns and then optimize how you basically take the virtual thing and you do something to it, and you use that feedback from what the virtual model tells you is going to happen in order to optimize the actions we should take in the real world to that physical asset. And then from there, this can all be used for training and learning, where we build out technologies that allow folks to understand the entire system's workings without actually messing with the physical thing that you're training on. So the common example, and this isn't a perfect example for a digital twin, but it's fairly close, and that's of a flight simulator, where we offer in a digital environment a detailed and realistic view of what an aircraft will do and how it responds to the environment in which it operates, right? So pilots use these all the time to kind of train on how a real aircraft is going to perform under a given scenario, right, in a safe setting. So they're not actually in the aircraft at the time. In the predictive maintenance world, this digital twin concept can perform kind of a variety of tasks for us. Number one, it can give us a comprehensive view of the data that's coming from the machinery, right? So we can actually view in the digital environment how that data interacts with the other assets around the thing that's being monitored, and give us a view that lets us immediately respond to changes in that data or issues that arise based on the data that we're seeing. We can also use digital twins for simulation and testing, where we've got different scenarios that we build out in the digital or virtual world, and then use those to foresee potential issues in the real world and evaluate kind of different strategies for what we should do if we see that scenario pop up in the real world. And lastly, you bring all this together. The idea is to optimize how we use our equipment using this virtual model to kind of perturbate and create like some scenarios that we can analyze and make decisions based on. All right, so if I'm right, yep, the kind of last part of this discussion, and I do have a few minutes left here to do this, we're going to do a quick demo that just demonstrates one slice of what we've been talking about. I'm excited to kind of do this demonstration because it's kind of a new technology that we've been working on. And we are definitely looking for folks who are interested in what I'm about to present and want to kind of get their hands dirty. We're looking for some early adopters of this technology to just come in for free and start playing around with what we're going to offer. So Nick's going to put a poll up on the screen just to see if you have interest in what I'm showing, and we'll reach out to you kind of in the coming days with early access to this Foreman AI technology. So before I get into that, I just want to kind of click through what it is we're doing inside Perceive. And I'm gonna focus the demo on one slice of this, but in general, what we're trying to do is help you collect data. That's the GraceSense line of technology. We have wireless sensors, we have capability to grab data out of PLCs and SCADA, that sort of thing. We want to be able to analyze that data in meaningful ways. So we do that a lot in the vibration space. We bring vibration data out of the sensors, and then we interpret that to give kind of identification of things that might be wrong in your facility based on the data that we're capturing. I mentioned this really early in the presentation. We do have some predictive models that we built with university partners that actually take that data and allow us to predict bearing failure, for example. These aren't ready to go live yet, but that's one of the pieces that we've been working on. And then what I'm going to be talking about today is actually helping you maintain your assets through the use of a Foreman explainable AI chat interface, which will give real-time maintenance help to a maintenance personnel. And then, at the end of this, I'll get into this a lot more on Thursday, but we really want to be able to bring explainable artificial intelligence technologies to the industrial space, and this is going to allow you as an end user of AI to better trust the underlying AI that you're using in your facility. So with that, I'm going to switch over and actually do a live demo, which is somewhat terrifying. If you've ever done a live demo, these things have a tendency to go off the rails, but we're gonna see how this works. So what you're looking at now is just our standard Foreman XAI interface for the maintenance-based chat. And what I'm going to do here today is just show you really quickly how easy it would be to get a maintenance kind of assistant up and running. The first thing we're going to do is we're going to create a new asset here. This is going to be let's just call it a pump 2. And I'm going to come in here and grab a pump type of kind of make and model that we're going to associate with that asset, right? So I've defined out the asset that we're talking about, and then the next thing we're going to do is we're going to actually give the AI a little bit more information than it has to start with in terms of how to maintain this asset. So if you've used ChatGPT, you could jump into that interface and start asking maintenance questions, and it would give you very generalized answers. But what we've kind of enabled here is the ability to create a chat. I'll call this just the webinar chat. And we're going to, chat about that new pump that I just created. And we're going to say, hey, AI, I've actually got a kind of a manual for that piece of equipment that I want to give you to augment your ability to kind of make decisions and give us some meaningful feedback from the queries that we're answering, right? So at that point, I've kind of loaded up the chat. It's ready to be able to give us some valid data. I've got this document loaded over here, this kind of bearing guide, which I'll pop up on the screen. And I'm going to say, let's say we have a problem, right? So my pump is running at 1800 RPM, and I'm seeing increased vibration at, let's say at 3600 RPM, so 2x the shaft speed, right? What is wrong? Okay, so one thing you'll note about any sort of generative AI, let me just make sure we're is that it does take a while for that AI to return. So instead of kind of sitting here and doing this all live, I'm just going to bounce to a very similar chat we had kind of earlier around a similar asset. So here's a very similar query we gave this. My pump's running at 1800 RPM. We've got an elevated radial vibration at 138 hertz. What are the possible causes here? Right, so our Foreman AI is responding and saying, well, here's some steps to address, that potential issue, and gives us a list of possible problems here. And these are all kind of coming from its general intelligence, but then being augmented by the AI that's kind of sitting behind the document that we've uploaded. So if I can get this to come up, here we go. It's going to spin here to check out. Let's say we're interested in, we think that maybe we've failed to effectively lubricate this particular pump. I can jump to the point in the guide that's actually going to kind of give me further information about that. And in this case, in this demo, we came down and we said, you know what, I think this is a lubrication issue, right? But how do I know for sure that it's a lubrication issue? And the AI then gives a set of steps that's going to allow us to kind of jump into that and assess whether that lubrication issue is actually the issue, right? So check the lubricant type, look at the system, look at the levels. I mean, in all cases, it's going to give us some citations back to that document that are going to allow us to kind of dig into that manual in greater detail. So, just to kind of burn through the rest of this. So we've done the maintenance. We see a potential blockage in the oil return hole, and then we say, I don't know how to fix this. What do I do? Well, the AI steps in and gives kind of a 6-step kind of guide. You're going to shut down the pump, access it, clean it, inspect it, and then it asks the user, hey, did this fix it? What? Tell us what happens when you do these actions. The user checks back in. Okay, we follow these instructions. Our vibrations return to normal. Is there anything else we should check to make sure that we've actually repaired the problem? And the AI gives a handful of kind of feedback here. You want to check the RPM of the pump. It gives some examples of how to do that. You want to monitor the vibration again, and then inspect for any new abnormalities. So the user does that and says everything looks great. And the kind of way that the AI exits in this case is to give you a total kind of a root cause analysis of what just happened. So it gives you a review of the initial potential causes, the primary causes that were identified out of the AI, and then some remediation steps that are taken from there. So that, at a very general level, is an example of a technology where we're bringing a couple of AI concepts into one thing to give an artificially intelligent partner to a maintenance technician. So again, if any of you are interested in actually getting your hands dirty with this technology, we're offering some free early access. Click on the poll here, or go to our website and kind of reserve or register for that early access there. So I think at this point, Nick, I'm going to just bounce my slide back up there so there's some content, contact information to be shown, and then we'll open it up for questions. Go. All right. Okay. So yeah, if anyone has, I'm going to do my best. We're getting used to using Teams as a platform, but please stick in your questions into this webinar, and I will go through these and try to answer any questions that pop up. Okay, all right, there's a good one here. Can AI be fed with old data in the system, or is it only run using real-time information? Almost always, that AI is going to be most effective if you train it on historical data. So, the best example of that is we're going to have years and years of information on some asset, and we're going to use that to train a model that understands how that asset behaves, and then we're going to feed it with data moving into the future and use that future data looking back on that historical information to make assessments based on the health of that piece of equipment. Now, that said, I know a lot of facilities we step into don't have historical data, right? So there's a couple of things we do there. Number one, if you're maintaining an asset, let's say it's a blower, your blower is unique in almost every way, but we can leverage training data that's been captured at other sites or from potentially that blower manufacturer in order to give a baseline for which we can look for problems, right? And then you're going to take that real-time data moving into the future, feed it into the kind of predictive analytics and make assessments based on it. So ideally, you have all the data in the world. In a common practice, you have no data. And so you kind of potentially set up and do some baselining for the first couple of months where you understand how a piece of equipment works, and then you use that to drive the analytics from there. All right. Nick's mentioned that. I appreciate anyone who said that was a good demo. I am very happy that the internet came back on and let me proceed. Okay. So I'm going to take a question about ROI. How do you know when the right time is to invest? And I'll talk about it from the condition-based monitoring and from the predictive maintenance perspective. How do you know when you're going to see a return on an investment on this sort of technology? What we typically work on with our customers is you really want to bite off a small piece before you try to instrument out your whole facility. So typically we work to find the most critical asset in a given facility, the one that goes down once a month and causes 3 hours of downtime once a month, right? That would be a good target for any sort of condition-based monitoring or predictive technology. If you know the downtime cost of that 3 hours of downtime, let's say it costs you $10,000 an hour in lost production, at that point, the very first time we prevent one of those downtime incidents from happening, that's going to basically be $30,000 that you're not losing. So you build a return on investment case based on that. And then, the idea is once that technology is in the facility, you start to find other applications where you can kind of build on that technology and create additional value. But in general, the biggest advice is, find that most critical thing, get familiar with the technology while applying it to that, and don't try to bite off too much because it is a lot to bring this sort of technology in. This is a good one. All right. What, in my experience, are AI's limitations? To be fair, that opinion has changed a little bit over the last year. I've seen AI advance in ways I wasn't expecting faster than I expected. But if we look at the generative AI, the big limitation right now is folks expect that to be able to kind of have a true rationalization about current events or facts when that actual generative AI is what it's doing is it's just predicting the next best thing that it thinks a human is going to say. So there are some limitations in terms of folks' understanding of how that generative AI is working and how it's trained. I think there's some limitations to these large language models. They can only be trained using tremendous amounts of resource. And right now we're still working into how that can be containerized on a smaller scale. I think that there's some kind of resource issues with both training and then executing these large language models on a large scale. In the kind of remaining useful life predictive area, the biggest challenge that we've run into over the last 4 years is just lack of good, solid failure data to work from. To give you an example, my background actually comes out of using this sort of technology to detect and predict failures in things like bridges, right? And you can't just go like destroy a bridge and take data from the destruction of that bridge. So that's true in the maintenance environment as well, where you don't want things to fail. So it's sometimes hard to grab that information you need to build a really elegant model that lets you do good prediction. So that data collection piece, that data exists, but it's kind of hard to get into a single space. So there's a handful of random things, but hopefully that kind of covered that. When do you question the answer that AI gives you? I mean, I tend to question the answer that anybody gives me all the time. I mean, even if I've got an expert in the room, I'm ultimately going to, agree with the expert, but I do not necessarily verbatim trust that I've provided all the information to that expert that they need to make an expert opinion. So that's true of AI as well. Just out of the box, I'm gonna question whether the answer that was given back is 100% accurate. Now, the beauty of this generative AI revolution that's really happened over the last 6 months is that I can actually probe on that answer. And that's one of the reasons why we've gone down the explainability path. One of the reasons why we've incorporated the document-based approach to this is that it gives the user some level of comfort that like this AI isn't just making stuff up. It's actually pulling this from this section of this document. And ultimately, if we can get to a point where the AI can explain itself in a way that a human would, I think the way I trust the AI is the same as the way I trust any other human in the way I interact. All right. There's a question about supply chain issues. Yeah, so AI I didn't talk about that today, but AI definitely has the potential to positively impact supply chain issues, both from predicting kind of an optimal inventory level perspective, looking at demand over time and kind of trying to forecast where that's going to go, allowing us to be more proactive on the procurement side. Let me just make sure that's basically the question that's being asked. If you can't get the parts, it would seem just as important as knowing when something's going to break. Absolutely, that's 100% true, right? If you're predicting that something's going to go down and you need the bearing from manufacturer X, that's got a 6-month lead time. Well, that's something that an AI could pick out as a potential problem. Now, our technology isn't focused on that space, but it's certainly a place where AI could create a tremendous amount of value. Yeah, okay. Next question's about response time. Anyone who's interfaced with ChatGPT knows, especially when it first launched, sometimes you couldn't even get in. Sometimes it would take 30 seconds for a response to come back. And over the last really 6 months, that has become more or less real time in a lot of ways. So in terms of timeline for getting to a faster kind of delivery point, I think that's just a matter of bringing the computational resources up to where we can use them. One of the things that I think you're going to start to see is the distribution of these models onto separate computing systems. So instead of leveraging a big cloud where everybody is grabbing information from the same point, you'll be able to deploy that model locally, and then your demand on that model is only as high as that inside your facility. So I think there's a variety of things that are happening to make that response from one of these large generative AI models or large language models quicker. But it's not a space I work in directly, so I don't want to be too firm on that point. Yeah, okay, this is an awesome question. How about distributed AI versus centralized? Is it feasible to perform runtime machine learning performance at the device? So interesting you asked that question. That's one of the things that we've done in this research. We have a low-cost wireless compute platform, our vibration and temperature sensor, and we actually have performed both training and kind of execution of a machine learning model on that wireless sensor platform. So the benefit of that distributed approach to this is that it allows us to not necessarily transmit wirelessly in a battery-powered environment all of the information that's required to train a model. We can do that training and that assessment of data locally, and then provide kind of predictions based on how long that asset has left in remaining useful life, we can provide just that out to the end user, and obviously that would be a tremendous saving on wireless bandwidth and the amount of time that node has to be on, which would give us the ability to do this in a battery powered package. Now that's not something that's ready for commercial use yet. It's something we've been kind of working on more on the grant side, but I do see the ability to perform distributed AI tasks as a major advance in a lot of cases where there are battery driven constraints, or you just have resource constraints in general with the amount of compute power you have access to. Is your data public? So I'm not 100% sure what that question means. I'll talk about data publicity a little bit. Let me see how I want to answer this. So at Grace, anything we do inside Perceive or at Grace, that data belongs to the customer. We have access to it to help perform our analytics and do the things that we do. But it certainly is not, like, customer data is not made public. And really the way that we build our AI models, there's no path for that data to ever translate into somebody else's hands. I think there is data that this generative AI world has raised a lot of data concerns, where when I provide anything into the internet, all of a sudden it generates out the other side as someone else's idea or someone else's creation, right, through the ChatGPT or generative AI path. That's something that there's no real good answer for yet. It's something that I think will need to be looked at over the next few years in a real serious way. Can AI do an assessment at the design stage of the project? So I'm going to answer that in kind of a tangential way. I think both condition-based monitoring and the kind of AI techniques I've talked about have a tremendous potential to aid the design process, not just the maintenance process. And the way that typically works is, if you have those data streams, it allows you to kind of loop back around with data that you get, feed that back into the design process, and iterate your designs in a more compelling way. So when we talk about kind of mechanical or even electrical or civil design process where you're using CAD to do something, absolutely. I know folks at Autodesk are looking at ways they can use AI to automate some of the work that they're doing. That could be done on the electrical CAD side. Certainly in the development of software. I mean, we heavily, our software team here uses AI-based tools to augment our coding when we're touching on that. So absolutely. I think there is a considerable amount of room to bring AI into the design process at the system level, at the equipment level, just across the spectrum in the industrial maintenance space. All right. So at this point, with part one, we covered the evolution of maintenance, kind of how maintenance has moved from a reactive world into a preventative world or a condition-based monitoring world. And then we discussed how AI and ML can really change that ecosystem into a truly predictive one. I also touched briefly on a demonstration of how generative AI can be used to assist a maintenance team in their maintenance tasks. And so we're going to kick off part two here by getting a little bit more detailed in our understanding of the technology behind what's been discussed, the challenges and the opportunities that kind of surround those applications and really the artificial intelligence and machine learning space as a whole. So that's enough of kind of introduction. Let's kick into the main content here. So for starters, and this is again redundant, but let's do another task at presenting what AI is and giving it some definition. So first and foremost, artificial intelligence is almost always going to come from a computer system of some sort that's going to be capable of learning from data, taking that data and the learnings that came out of it and making decisions, and then ultimately performing some sort of task that has historically required human intelligence to complete. So just to reiterate, it's a computer system that's performing some task that used to, in our past lives, require a human, at least in some capacity, right? And there's a lot of ways we can apply this in the predictive maintenance domain, from predicting machinery failure to recommending kind of maintenance tasks to interpreting image or video in our facilities or understanding, natural language on a conversational level. And today, what we're going to do is dive into kind of some of the underpinning tenets that sit underneath these applications. So I'm going to start by talking about 5 kind of what I consider to be main topics or main ideas that are prevalent within the AI space. And I think it's important to understand each of these in at least a little bit of detail to talk about artificial intelligence or machine learning in detail. So the first of these, and we didn't really talk about this in part 1, but is machine learning. We'll move on from there and talk about neural networks, then talk about how deep learning plays into that ecosystem, and then finish off by talking about classification and regression problems. And then from there, we'll move on to talk about some opportunities and challenges. All right. So machine learning. This is a subset of artificial intelligence that's going to provide our computing systems the ability to automatically learn and then improve upon their learnings based on experience that's coming from data without a programmer sitting there and explicitly programming that knowledge into that computing system. So we use statistical methods, and then we enable those machines to actually improve with experience. So we break this down typically into 3 main types of machine learning. The first of these is supervised learning. In this particular approach to machine learning, we take a machine learning model and we train it using a data set that's labeled. So a good example of this is your spam filter. If your spam filter has been built using machine learning tenets, we basically, what has been done is a set of email has been provided to it, historical email, and each email has been classified either as spam or as not spam. And then the machine learning model is going to pull the new email that comes in and assign a label, either spam or not spam, depending on kind of that historical that historical knowledge that we're building from the data that's come in on those previous emails. We okay, Nick? Okay. All right. Second main machine learning type is unsupervised learning. So this is the flip side of a supervised approach where we're going to actually train a model on an unlabeled data set. So we need to actually use the machine learning techniques themselves to find patterns in this data on their own. So a good kind of common example of this is Netflix or Amazon making recommendations based on previous use case from that user. So if I have previously bought products X, Y, and Z on Amazon, and the machine learning algorithm can actually look statistically at what other users who have kind of bought those products and potentially fall in a similar demographic group to me have bought, it's able to make inferences on what I might like to buy next based on that kind of set of unsupervised data that it's been given. So there is no actual classification happening. It's using similarity concepts to drive its training process. So the last kind of main type of learning that you'll encounter in the machine learning space is reinforcement learning. And this is what's been used heavily in a lot of the kind of game-based development. If you see an AI that's playing some sort of game, more often than not, it's been trained using a reinforcement technique. So this is where that model is going to interactively learn with its environment by receiving either rewards or penalties or both based on the actions that it takes in that environment. So examples of these are DeepMind's AlphaZero and AlphaGo, which are capable of learning from scratch how to play complex games, in this case chess or Go, just by playing hundreds of thousands or millions of iterations of a game and being rewarded when they make a good move and being penalized when they make a bad move. And those rewards and penalties over time can serve to train a machine learning model to actually play these games at a level that's greater than any human. And so this is a very powerful way for training certain types of machine learning models. All right, so the underpinnings of machine learning generally sits in this concept called a neural network. I'm sure you've heard this term, but I'll get into a little bit more detail here. Again, surface level, but more detail than you'd have if you haven't seen this concept. So a neural network is a computing system that's been inspired actually by the human brain. That's why we call it a neural network. These networks are composed of layers of neurons. So on this image that I've got here, each dot is a neuron in that network. And those neurons are responsible for either processing or passing on or doing both information that's kind of coming from left to right in this network. The key components to this any sort of neural network is going to be the input layer. So this is where we're taking our data stream and we're gonna push it into the network, whatever that data stream might be. That could be my shopping history, for example. We then have a set of hidden layers. These layers they sit between the input and the output, and they're generally used to perform kind of simple computations that are going to transfer information from the left to the right. I mean, we'll get into a little bit more detail about this later, but the idea is that these computations are what get trained in this network. Then on the right side of any neural network, you see your output layer, and that's going to be the results that the neural network is providing. So in the case of my shopping example, I put my shopping history, for example, on the left side, and out the right is going to give me some suggested products to buy. That's how this network works. And then when we train one of these neural networks, this is the process by which we adjust the parameters in those hidden layers using kind of known inputs and known outputs, depending on which kind of learning technique we're using. And in the end, what we're trying to do is produce accurate outputs for a given set of inputs, right? I want when I put my shopping list in the system, I want to be able to get a good set of recommendations out the other end. So the goal of any sort of training is to create a network that reflects reality as closely as possible and gives the best possible predictions in as many cases as possible. So if we take the neural network and the machine learning concepts and kind of drive them in a application or application specific way, we end up inevitably talking about deep learning, which is another concept I'm sure you've heard in kind of common parlance over the last few years. This is a subset of machine learning where we're using neural networks to learn from vast amounts of data. So in some simple neural networks, you could have only one or a couple layers, but generally in a deep learning system, we're going to have potentially hundreds of layers that are going to allow us to learn and then execute on super complex patterns in data. The kind of applications that we see here, specific to predictive maintenance in this particular case, are pattern recognition. Okay, so these deep learning networks are capable of really recognizing complex patterns in machinery performance or the sensor data that's coming in, and we can use that deep learning network's understanding of those patterns to detect when things are wrong, right? Secondarily, we can do advanced predictive modeling. So we can create really highly accurate models because of the number of parameters that can be trained inside these models. An example of that, if you look at OpenAI's ChatGPT, I mean, there are potentially trillions of parameters inside that model that are being trained, and that allows it to perform in an incredibly complex way. And we can also do really advanced image or sound analysis, where we take visual or audio input, and we're detecting issues that maybe are not easily captured by traditional sensors. So this, in addition to some of that generative kind of AI stuff I talked about in part one, these are major applications for deep learning. All right, so next kind of concept I want to lay on the table is classification. And we did talk about this in part one a little bit, and it's been mentioned offhand, and I think it's fairly intuitive to folks what this means. But classification is generally going to be a type of supervised learning where the output is a category or a class. So in the predictive maintenance space, that's typically you're looking at, healthy, not healthy, right? Or healthy, kind of healthy, not healthy. These categories can be anything, and they can be as numerous as you want. But the idea is we're building classification algorithms that are going to take training data and use it to classify new observations into those classifications that we've set up. So my example here is basically a very simple classification problem where we're trying to figure out if a dot is black or white, right? And you can see in both of these images on kind of one side of this line, the dots are black, and on the other side, they're white. So what the classification approach is doing is it's trying to find where to place those lines so that when the next dot comes in, it's pretty obvious which category that particular dot falls in, the black or the white. And this gets significantly more complex when you have, kind of more than two axes in this particular problem. But for now, just think about it like this, in a kind of two-dimensional way. And what we do a lot of times is we try to take that boundary, which is squiggly on the left, and then find mathematical ways to represent it as a very clean boundary, like you see on the right. And that enables us to do our classification in a much, much easier way. So there's a lot of ways I'm sure you can see that this is used in the predictive maintenance space. First and foremost, fault diagnostics. I already talked about that, categorizing things as either healthy or not. We can also use data that's coming in from our equipment and basically categorize the risk level of that piece of equipment failing based on the information that we're seeing. So this allows us to do a risk-based analysis of where our maintenance needs to be headed. And then the last thing here is actually using a classification approach to recommend certain maintenance actions. So if you were to train a model on the optimal maintenance approach for a given set of input data, we could actually, the output of that could be just a straight recommendation for some sort of maintenance. And that would be the classification is either no maintenance or, lubrication, you need a bearing change, you need an alignment, whatever the issue is, we can classify in that sort of way. So this is one major way in which machine learning specifically is being used to drive artificially intelligent systems. So I'm going to give a very specific example here, and this comes from the research that we at Perceive have been doing with Iowa State over the last few years, where we're really trying to, in this case, classify what type of damage, if any, a specific rolling element bearing has been seeing. Right. So this is an example of a deep learning approach to classifying bearing damage. So if you look at a bearing, like I've got shown here on the screen, there's kind of several ways in which this particular bearing could see degradation or damage. And it generally occurs by some sort of cracking or pitting in either the ball itself in that rolling element bearing, or the inner race, the outer race, or the cage. Those are kind of the three main ways in which a bearing can degrade. And so our research here was really looking at, okay, can I take vibration data from that bearing and be able to classify whether that bearing's healthy, whether it has an inner race fault, an outer race fault, or some combination of these kind of different types of faults that we can see. I'm not going to get into this kind of image at all, but you can see here the way that works is kind of this physics-inspired convolutional neural network. And this particular network is a layered system that allows us to take that vibration input data, filter it in a very specific way, and then output a health class on the right side of the network. And in the end, this very simple kind of test matrix you see at the bottom, this is how we kind of validate whether this is working. So we run a bunch of different examples. On the left is the true label, the actual health class of the bearing that we're talking about. And on the top is the predicted health class. And you can see that in this particular example, in almost all cases, our physics-inspired convolutional neural network, was able to identify which health class the particular bearing we were monitoring existed in. Now, I will say that this was done under very clean data, so you generally don't see 100% success in these systems. And we, if you're interested in that paper, reach out to me. We can push you to the more complex analysis we did. But this is generally how a generic classification problem would work. All right. So moving from classification to kind of the other type of main output in the predictive maintenance space, this is when we start talking about regression. So this is a type of predictive modeling where we're going to estimate a relationship between one variable, a dependent variable, and one or more independent variables. So you can see this plot on the right where we've got a bunch of data. The idea is to, if I know my Y value here, to be able to predict the X value or vice versa, depending on the application. And the goal here when we're doing regression is to be able to kind of match that curve and then predict a continuous outcome from where that data sits over time. So where can this be used? This has kind of been talked about quite a bit in the last couple of parts, but we can use regression-based techniques to forecast the remaining useful life of industrial equipment. Right? This is using historical data to then train a model on what that data is going to look like moving into the future. That's a regression-based approach. We can do the same kind of thing for inventory levels, right? And this was brought up in the Q&A session in our last part, where it's well and good that we can predict when something's going to fail, but if we actually can't predict whether we're going to have the replacement part in time, that may defeat the purpose of predicting the failure in the first place. So I think there's a lot of applications that are going to start to emerge for AI and ML in inventory management and supply chain applications. And then lastly, I think regression can be a really powerful technique from a maintenance perspective when predicting the costs associated with a maintenance program. So this allows us to do a better job of budgeting for what maintenance is going to look like over a period of time, and then along with that budget, planning out resource allocations and scheduling maintenance and all of that. If we have a solid AI-backed way to forecast our cost structure moving forward, it makes a lot of these more kind of business level decisions a lot easier. All right, so here's an example of, again, some of the research we've been doing with Iowa State over the last few years in its ability to predict the remaining useful life of bearings. So this was a deep learning approach, again, not to classifying the health of a bearing, but to actually predicting what's going to happen to that bearing in the future. So when you're looking at this plot, I want you to first focus on kind of this top plot. This is showing the overall vibration level of that bearing that's under test. And that vertical line you see, it's kind of a dashed vertical line. Think of that as right now. So everything to the right of that is the predictions that the model is making. So up at the top, we're going to have some sort of maintenance threshold. And if we're doing condition-based maintenance, typically, we've got these thresholds and we're going to alert a user when that trend hits that threshold. So the difference here is that I'm not waiting until I hit the threshold to alert the user. I'm telling the user, hey, there's a chance that you're going to hit this threshold in the next 45 to 60 days, right? And our predictive models are showing, that probability of threshold level exceedance is going to fall, kind of in that 1 to 2 month window, right? Now, the next thing I want to pull your attention to is the second plot there, the green one. This is the part of the vibration analysis that relates to the lower speed or the shaft speed related dynamics. And you can see here that our predictions are that is not changing drastically. We don't expect that to ramp up much in the future. And that the information that we get from that is that, yeah, you're going to need to maintain this piece of equipment over the next kind of couple of months, but it's probably not an alignment or balance problem, right? If we look at the bottom plot, however, which is focused on the higher frequency dynamics that typically relate to bearing problems, we can see that those dynamics do trend with that kind of 45 to 60 day window. And in this case, we can say fairly confidently that it looks like this particular bearing is going to, this particular piece of equipment is going to experience a bearing problem over that kind of 45 to 60 day timeline. And obviously, if you're running a maintenance team and you have the ability to forecast that out, it makes it a lot easier to plan when you're going to maintain that piece of equipment. All right. So the rest of this presentation, now that we've kind of taken some time talking about the nuts and bolts, is going to focus on what are the remaining hurdles to kind of take this sort of AI technology into practice in the industrial space. And I won't talk about these on this slide because we're going to touch each one in greater detail over the next maybe 10 minutes here. So let's start with implementation costs. This is one of the big issues right now with getting started with AI in the industrial setting. The initial setup of any AI ML system is going to be expensive, almost certainly. And it's going to require upfront capital to get moving. There's just no way around that because it's generally new technology. It is also going to require ongoing maintenance costs to keep it running effectively and efficiently, and even more than that to run it optimally. Right, so we're going to need to pay for system updates, for data management. We got to train users to be able to effectively use it. So there is an ongoing cost to any sort of AI ML solution for sure. And one of the things we run into with our customers a lot is it's very difficult a lot of times to put a good return on investment number on an AI ML implementation. It's not necessarily immediately clear what that AI is going to do, and that may make it hard to put that kind of upfront money on the table. So I'm going to turn that around, though, and talk about opportunities. Right? Let's say we take this hurdle. It's going to provide, a variety of benefits to that company. First and foremost, long-term savings. Predictive maintenance in general can lead to enormous cost savings just by predicting catastrophic failures before they happen. The typical example here is if you have an application that costs you $10,000 per hour when it's down, and it's down for 3 hours every quarter, right? Well, if you're able to prevent one downtime incident and that system costs $30,000, it's paid for itself. Secondly, using AI ML for predictive maintenance can really improve efficiency. So in addition to just detecting these errors, it can help point out better ways in which we can maintain our equipment, which will lead to overall improvements in operational efficiency, which coincidentally also help with cost savings and increased profits overall. And then lastly, I think the first movers in this AI ML space, at least those first movers that are able to effectively implement AI and ML in their kind of industrial worlds, they do have a competitive advantage because it will give them a leg up in a variety of ways over their competitors that don't have access to that same kind of technology. So implementation costs are challenge number one. Challenge number two is technology integration. And this has been the case with all of the condition monitoring technology that we've seen at Grace. It continues to be with AI and ML. How do we actually integrate these new technologies with our existing legacy industrial systems? The main issue here is that existing infrastructure, especially in the industrial world, is almost certainly not compatible with new AI and ML technology. Especially today, if we look at it right now, there hasn't been a lot of movement to try to bridge that gap. So you tend to see the AI ML technologies being developed in a bubble outside of the industrial world. And as a result, that's going to require complex or costly updates to existing systems in order to get everything integrated. There's also almost certainly going to be a skill gap in the industrial world where most manufacturers lack the in-house technical skills necessary to easily integrate these new systems. There's going to have to be new training on how to use this stuff, and none of this is rocket science, but it does require a change of focus from kind of the way that maintenance has been running over the last several decades. And then ultimately, generally, when you put in a system that's this kind of earth-shattering, you will see disruptions of current processes. Implementation of new technologies can almost always establish, routine workflows and force the maintenance workforce to do things differently than they have historically. But if we turn that on its head, it really, I think, this technology has the potential, if properly integrated, to really streamline that maintenance process, which in the end will reduce downtime and improve on efficiency, like we talked about in the last slide. I think it allows us to make better decisions as those responsible for maintaining assets. If we can integrate this properly again, we can provide comprehensive real-time data to the maintenance team, which ultimately aids in the best decision-making possible if you know what's going on in real time, and even better if you know what's going to happen in the future. And ultimately, an AI ML system kind of sets the stage for continuous improvement. If we integrate this level of technology now, that really will be a first foray into the ability to kind of continuously integrate on this technology as it moves out, as new tools and new techniques become available. So that's challenge number two. Challenge number three relates to data, and specifically the quality of that data and the management of that data once it's collected. The problem that we typically see with data collection is that it's either inaccurate, it's bad data coming from sensors, or it's incomplete. And if we have either of these scenarios and that data quality is poor, that your artificial intelligence is only as good as the data that you're pumping into it. So if you have bad data, it's going to lead to bad predictions, bad classifications, and ultimately suboptimal decisions. We also run into a problem with data where it's siloed. So you may have multiple systems collecting data, and that data is not integrated well. If this is the case, we also run into inefficiencies because that AI really functions best in most cases if it has a comprehensive view of how the ecosystem is functioning that it's monitoring, right? So getting data into a single data lake is an important part of an effective AI/ML implementation. On the flip side of that, right, if we successfully get this data collected, that high quality data can really improve the accuracy of any AI/ML model, and it will lead to better predictions. A lot of times, quality data can actually overcome an AI model that's maybe not the best, because that AI model, if the data is clean, that technology is pretty capable of making good assessments based on data that's coming in. Another opportunity here is just holistic insights. If we have good quality data that's managed properly, it's going to enable our comprehensive analysis of everything across the facility, right? So even if we're focused on monitoring some sort of critical blower, for example, getting this technology in place will eventually allow for a comprehensive view of how the facility is operating, and ideally, that comprehensive view will provide some holistic insights that drive value across an organization. And then lastly, if we have good data, it's going to aid the trust of anyone who's kind of looking at that data. So if we have compliance requirements that enforce the need for good data, or if you've got a maintenance technician or a maintenance manager or an executive that's looking at an AI-based system, if that data is clean, correct, and well stored, it's pretty easy to point back at it when you look at the results of an AI/ML algorithm and say, look, the human can make the same assessment as the AI. If the data is messy, it gets a lot harder to kind of draw that together. The AI becomes a little bit more of a black box. So this challenge here, the fourth challenge, is related to the last one because it deals with data. And here we're going to talk about cybersecurity. So first and foremost, I think as we collect more data, this is true of condition monitoring as well as AI/ML, the more data we have, the higher the risk that there is a breach of that data. Now, in the kind of condition monitoring or AI/ML space, we're not dealing with personally identifiable information generally. So, maybe this is not as critical, but we do have customers that are very concerned about the privacy of their equipment data because of potential competitive issues or other reasons why that data needs to be containerized inside a facility. So this is a challenge that needs to be overcome. Additionally, we're starting to see regulation emerge that's going to require companies to protect certain types of data. And if you fail to comply with those regulations, that can result in both hefty fines or other public kind of ramifications. Now, again, in predictive maintenance, this is maybe not as critical as other spaces. One of the places this is popping up is, let's say you have an AI that's helping an insurance company choose whether or not to insure something. This is a place where regulation may require that insurance company to make sure that its data is maintained privately. So on the flip side of kind of the hurdles of getting involved with a quality cybersecurity practice, this does give any user a competitive advantage. If you're able to put in a truly secure data lake, this will demonstrate compliance with any sort of regulations that apply, but also just give your customers kind of peace of mind knowing that you are able to deal with data and perform these kind of advanced analytics in a way that's reliable and trustworthy. There's also an opportunity in some emerging technologies. So I was going to talk about this and then decided not to, but there are some mechanisms evolving, federated learning being one of them that we've played around with a little bit, that are going to enable AI and ML approaches to exist without data sharing between entities. So to give the example there, if you have two plants and you've got data from both of them that might benefit the building of some sort of predictive model, we can actually use a federated learning approach to train those models locally and then have those models kind of coordinate up a level without actually sharing any sort of identifiable information that went into the training between plants. So that's kind of one of the things to look for in kind of the coming years are these abilities to decentralize training to protect data. Okay, this is my last topic here, and it's the one that maybe is the most kind of influential to me, the one that's top of mind for us here at Perceive and Grace, and that's this challenge of explainability. So when we talk about AI in general, models have a tendency to be very complex, especially when we're dealing with deep learning. And those models, as a result, are super difficult to interpret. So if I classify this thing as healthy, it generally is very difficult for a human to go back to that model and figure out why the model said that this thing is healthy, right? That takes a lot of effort. There, on the explainability side, there's also this trade-off between accuracy and explainability. So if I have a highly accurate model that's giving me excellent results, that tends to be a more complex model, and as a result, it's less interpretable. So there's this like trade-off between I want it to be super accurate and I want to be able to understand why it's making the decision that it's making. And lastly, I think there is going to be a regulatory challenge here as well. Certain industries are starting to put regulations in place requiring a level of explainability. And this may make it challenging in some places to implement AI models. Now, I don't necessarily see that happening in the predictive maintenance space, but let me go back to my insurance example. If we have an AI that's aiding an insurance company in making a decision about whether to insure someone, there are regulations starting to emerge that are enforcing the fact that decision is being made without any sort of discriminatory practice underneath it, right? So if that model is somehow using protected information to make that assessment, and there's no way for that insurer to point back at the fact that that model's not doing that, that's potentially an issue in that space. So again, I don't see that playing out quite that way in the predictive maintenance space, but it's one that you should be kind of aware of as AI continues to take off across industries. So on the flip side of these challenges, an effective explainable AI approach can definitely generate trust and confidence in users. And this is huge in the predictive maintenance space. So if we've got maintenance technicians or maintenance managers who truly understand the decisions that are being made by the AI model, that makes that AI partner more of a trusted resource and less of a black box. So it also, by explaining these models, that inevitably is going to lead to better model development. So if our models can do a better job of explaining how they're making decisions, that allows the human to kind of come in the loop and help improve the design of the model and the ultimate performance of that model moving forward. So explainability is a big topic. I'm going to throw a slide. Oh, I got one more here. Regulatory compliance. I mean, this touches on what we just talked about, but in industries that have these regulation requirements, obviously, if you don't have explainability involved, you might not be able to play with AI in that space. So it may be a requirement. Okay. So last thing I'm going to do here is give kind of a quick example of one of the ways in which we've played with explainability in this kind of bearing world that we've talked about. So explainable AI, XAI in general, is going to refer to methods and strategies in the application of some sort of AI that's going to result in that AI solution being understandable by human experts, right? So this is in contrast to the more black box approach to AI, where you have a neural network that's taking in input and putting out some output, but there's no way to understand or interpret what's happening between input and output. So the idea here is really we're driving that level of trust in the human. So in predictive maintenance, this is going to allow us to understand decisions better. Operators, decision makers can better understand what the AI is doing and make decisions from there. It's going to let us verify the soundness of our models. So if you're a expert that's actually helping create the model, the explainability piece of the puzzle is going to allow that expert to examine the logic behind the AI model itself and ultimately increase the confidence in that model's validity and reliability. It's also going to, explainable AI will provide explanations that allow it to align with the technician's experience and expectations, right? And if we do this, this is going to help build trust in that technician in, that the model's outputs moving forward. And then lastly, if we have explainability as a main piece to any AI system, it's going to drive AI models that can be communicated more efficiently between maintenance workers, between maintenance to management, and kind of all the way across the organization. So one example, just to give you a little bit of context of how this works. This is a paper that came out of Nature's Biomedical Engineering journal. This was a few years ago, and we've been using some of these concepts in the bearing world, but I think it's easier to see in this environment. So this is a set of intracranial kind of X-rays, right? So these are scans, CT scans of a human skull, looking for signs of intracranial hemorrhage. And I'm not going to get into any of the medical because I don't understand it. It's not my world. But imagine that there's kind of two types of hemorrhage that you can have here. You can have a red hemorrhage or a blue hemorrhage, and you're seeing at the top there that over the set of data that they're looking at, they're classifying a probability that a given image has a given type of hemorrhage. In this case, the blue is up in the blue section, the red is up in the red section. It travels right with that, right? So you have a visual probability of that classification, right? And this could go to a doctor. You could put your image into an AI system and it would say, hey, you have a 100% chance that you have a blue hemorrhage, right? But that's potentially difficult to trust if the doctor doesn't know why that decision's being made. So this paper goes in and it actually uses kind of a visual explainability method to show that doctor, that physician, the rationale behind the AI's decision. So the first kind of level of this is it's going to visualize the locations of what it's pulling out of the image that's being analyzed. So that's this first kind of layer here, is it's saying, hey, these areas of this scan are what are concerning to me. And then the second stage is it's going to drop down and it's going to pull similar scans and show the doctor, look, this was a case in which this was a blue hemorrhage. And let that physician look at the difference between the image that they're looking at for the patient they're examining and potentially other images that are related in diagnosis to the one that the AI is presenting. So as a whole, this level of explainability is giving that medical professional greater trust in the AI that sits alongside them. And the same concept could be used in really any application, but I like this one as a potential game-changing type application. Yeah, so that was that last piece there. To kind of wrap up the conversation, I did a demo of some of our new kind of perceived technologies in the last part, but here I just want to touch on where we're headed, and really what we're looking for at this point. We want to start a conversation about how AI and machine learning can have a positive impact in the industrial space. So Nick's going to put a poll on the screen here. That's going to kind of just show if you're interested in kind of early access to any of the technologies that I'm kind of going to talk about here. Specifically, we do have a generative kind of AI-based chat assistance for maintaining industrial assets. But when I look at explainable AI in general, I look at it in kind of 5 main pieces. With this technology, we hope to better assist the industrial world in collecting data. We do that already with our GraySense line of products, providing wireless sensors that can capture data from pretty much any industrial asset and bring that to the cloud. But we also can bring in data from a SQL database or a PLC or a SCADA. So that's kind of thing number 1. Thing number 2 is we want to help analyze that data. So again, our focus historically has been on vibration-based problems, detecting issues in either bearings or other kinds of rotating defects that occur in those sorts of assets, and then being able to provide that as an additional level of information to the sensor data that's being gathered. From there, we hope to bring those kind of predictive algorithms I talked about earlier into commercial practice, so you can take that data that you've been gathering and do forecasting for how that particular piece of equipment is going to perform in the future. The 4th bullet point is assisting kind of our customers in maintaining their assets. This is the demo I showed last time, where we can bring conversational AI alongside a maintenance team to give them a better ability to identify defects in their facility and then resolve those defects and lastly report on kind of that root cause analysis or remediation actions that were taken to fix that problem. And lastly, this couples with what we just talked about with explainability. We aim to help customers trust their AI, right? So building out tools that are going to help provide clear and concise model explanations for any AI in that facility. So again, this is a long path. This is not a fully articulated solution at this point, but we're looking to start that conversation with folks moving forward. So with that, I'm going to stop talking myself, and we'll see if there's some questions here that folks would like to have answered. So let me pull up the chat bar. Okay. So first question I'm seeing here: do Netflix and other social media have reliable machine learning sites? So I'm assuming that question is whether. Well, I'm going to answer it in twofold. I'm not sure which way this went. So first of all, they have a tremendous amount of data. And access to a tremendous amount of data makes the underlying predictive algorithms better. Now, that said, they also have a rather open-ended problem that they're trying to solve, where they're giving recommendations. So being able to deploy that effectively, I think we're all familiar with the level at which these sorts of content recommenders can do what they do. In terms of data reliability, I can't answer that. I would assume that they are under watch, and all your data is kept as private as possible. But I can't speak for those companies. A question that kind of follow on there was, our inputs, do they have a minimum amount of data necessary for an input? That's a good question. I'm not sure I touched on that, at least in this part 2. The more data we have to build a model, the better. And in a lot of cases, specifically in the predictive maintenance case, we just don't have enough data. We don't have enough failure information to be able to build a really sophisticated model that's able to do a super accurate job of predicting failure. There's a lot of techniques to aid that. We use a physics-inspired approach that brings physics into the equation and lets us run with less data than we might otherwise need. There are data augmentation methods that allow you to take what data you have and build kind of synthetic data that sits on top of that to make better decisions. But in general, the more data you have and the cleaner that data is, the easier it's going to be to build a really effective AI platform. So yeah, this is a good question too. If we have data from a different plant, is it applicable? The answer to that is maybe. So if you have 2 exact assets, I'll talk about vibrating assets right now. If you got a pump in plant A and a pump in plant B, and they're exactly the same model pump, it is very likely that a model trained in plant A will be able to give you beneficial results in plant B. However, there is almost certainly a difference in the operational environment between those 2 plants, even if it's almost the same application. And so ideally, we can leverage the difference in environment and be able to kind of fine-tune the model that we've got over here to fit in this new environment. But it really, depends on the level of accuracy you're looking for. And I will say, if you're looking for 100% accuracy, you're almost always going to have a problem. So, all right. Okay, can AI recommend a work intervention to equipment in order to extend kind of the prior to failure phase of that equipment? The short answer to that is yes. We don't have a technology that does that specifically, but if you think about an artificially intelligent system that learns in the same way you would maybe learn how to play chess, right? We have an action that we could take to try to prevent or obtain some sort of reward in the future. In this case, we're talking about taking a maintenance action. And if we have sufficient number of maintenance logs to build a machine learning model that can say, all right, this action given this data set leads to an optimal outcome, absolutely. The output of that model could certainly be, you need to take this action and there's this degree of probability that prevents this problem. So that is definitely an application. Again, data availability for building that model is probably the biggest reason why it'd be hard to get there. Yep, there's a mention there about lack of trusted labeled data. So that's anytime you do classification, right? That's what I'm just talking about with this maintenance recommendation system, right? If you don't know the labels on the existing data, so it's just a jumble of data and no human has come in to effectively curate it, it does make it very difficult to build these models as effectively as possible. Right. Am I missing anything there, Nick?
Nope, I think you covered everything.
All right. Okay, well, seeing no more questions, I really very much appreciate everyone joining us on this two-part journey. If you have interest in anything that we've been talking about, please reach out to us. We'd love to interface with you on kind of a deeper level. And again, this is an exciting new field, one that we're excited about, and we'd love to have chats with anybody who thinks they have an application that might work here. Yeah, we'll leave it at that, and we'll get the on-demand videos out in the near future. Very good.